What if the story of our universe's beginning is even stranger, more mysterious, and more awe-inspiring than we ever imagined? From the fiery birth of time and space itself to the hidden forces and phenomena shaping the cosmos today, the origins of the universe hold secrets that could completely transform how we see our place in existence. In this video, we're diving into 25 forgotten facts about the universe's origins. Facts that don't just add layers to the story, but challenge the very way we think about everything. Some of these will leave you scratching your head. Others might give you chills, but each of them will bring us closer to unraveling the mysteries of where it all began. So buckle up, because the journey to understanding the universe's secrets starts right now. And trust me, you won't want to miss a single moment. Now, turning to our first astonishing fact, let's clear up one of the biggest misconceptions about the origins of the universe. Contrary to popular belief, the Big Bang was not a colossal explosion ripping through pre-existing space. Instead, scientists describe it as a rapid expansion of space itself, where the universe sprang into existence and began stretching like an inflating balloon. Picture this: imagine dots drawn on the surface of a balloon. As you blow air into the balloon, the surface expands and the dots move further apart, not because they are flying away from each other, but because the balloon's surface is growing. This analogy helps us visualize what scientists believe happened in those initial moments. The Big Bang wasn't about something exploding into empty space. It was about space itself being created and expanding everywhere all at once. This understanding shifts how we think about the universe's birth. It wasn't chaotic destruction, but the start of a fascinating, orderly process that gave rise to everything around us. And with this clarification, we're just beginning to see how intricate and amazing the universe's beginnings truly are. Moving forward, let's unravel another surprising truth about the universe. Unlike what our everyday experience might lead us to believe, the universe doesn't have a central point of origin. When we think of something expanding, we often imagine it growing outward from a specific center, like ripples spreading from a pebble dropped into a pond. But the universe's expansion doesn't work that way. Scientists describe it as uniform, meaning every part of the universe is moving away from every other part simultaneously. To picture this, think of a ball of dough filled with raisins. As the dough rises and expands, the raisins move farther apart, but there's no single raisin or spot in the dough that acts as the center of the expansion. Instead, the entire dough expands evenly in all directions. Similarly, no matter where you are in the universe, it seems like everything around you is moving away. This uniformity, known as cosmic isotropy, is both fascinating and humbling. It challenges the way we intuitively think about space, because it means there isn't a central point we can call the universe's starting location. Instead, the universe's expansion is happening everywhere all at once, like a vast and ever-growing fabric. This idea not only reshapes how we understand the cosmos, but also encourages us to think beyond the limits of our earthly perspective. And just when you think it can't get more intriguing, the next layer of the universe's origins offers even more to explore. Now, turning to one of the most compelling pieces of evidence we have about the universe's origins, let's talk about the cosmic microwave background radiation. Imagine this as a faint, almost ghostly afterglow left over from the Big Bang itself, a kind of fossilized light that has been traveling through the cosmos for billions of years. Discovered by accident in the 1960s by scientists Arno Penzias and Robert Wilson, this radiation was initially just an unexplained noise in their radio telescope. Little did they know they had stumbled upon one of the greatest discoveries in cosmology. This faint radiation is like a time capsule, giving us a glimpse into the universe when it was just a few 100,000 years old. Back then, the universe was a hot, dense plasma, and as it expanded and cooled, this light was released, spreading across the cosmos. Today, we can still detect it, though it has cooled significantly to just a few degrees above absolute zero. What makes the cosmic microwave background radiation so important is what it tells us about the early conditions of the universe. Scientists have mapped this radiation in incredible detail, revealing tiny fluctuations that correspond to slight differences in density from the time when the universe first began to take shape. These fluctuations are the seeds from which galaxies, stars, and planets eventually formed. The cosmic microwave background provides crucial support for the Big Bang theory because its very existence aligns perfectly with predictions made by the theory's models. Without it, our understanding of the universe's beginnings would be incomplete. This glowing relic from the past continues to remind us of just how far we've come in uncovering the story of the cosmos, and yet it also hints at how much more there is to learn. And speaking of the early universe, there's another fascinating aspect of its origins waiting to be explored. Moving forward, let's dive into a time when the universe was an unfathomably hot, dense plasma, a period where the cosmos was far from the structured beauty we see today. Picture this, an energetic soup of particles with protons, neutrons, and electrons zipping around in a chaotic, high-energy dance. During this plasma phase, temperatures were so immense that these particles couldn't combine to form stable atoms. Instead, they collided and scattered endlessly, creating a state of perpetual turmoil. Light, which today travels freely across the universe, was trapped in this fog-like environment, bouncing off particles and unable to escape. This meant the universe was not transparent. It was more like a glowing, impenetrable mist. As the universe expanded and cooled over hundreds of thousands of years, this plasma began to settle down. Eventually, the temperature dropped low enough for protons and electrons to combine, forming the first hydrogen atoms. This monumental moment, often referred to as recombination, finally allowed light to travel freely, marking the end of the cosmic fog and giving birth to the universe as we know it. This shift not only cleared the way for light to illuminate the cosmos, but also set the stage for the formation of stars and galaxies. It is astonishing to think how this chaotic beginning ultimately led to the incredible structures and beauty we observe in the universe today. And as we consider the next steps in this cosmic evolution, the story gets even more intriguing. Now turning to the next phase, let us explore the formation of the very first atoms in the universe's history. After the tumultuous plasma era settled and temperatures dropped further, the universe reached a point of stability where protons and neutrons could come together to form atomic nuclei. This process, known as nucleosynthesis, was crucial in shaping the foundation of our cosmos. The simplest and most abundant element, hydrogen, was the first to take form. Comprising a single proton in its nucleus, hydrogen became the building block of all matter. Alongside hydrogen, helium atoms also emerged with their nuclei containing 2 protons and typically 2 neutrons. These 2 elements dominated the early universe, making up almost all the matter that existed at the time. Interestingly, there were almost no heavier elements, as the conditions then were not extreme enough to forge more complex nuclei. This early chemical simplicity might seem unremarkable at first glance, yet it set the stage for everything we see today. These light elements served as the raw material for stars, which later acted as cosmic factories, creating the heavier elements essential for planets, life, and the intricate structures of the universe. Without this critical phase of atomic formation, the cosmos would have remained a formless expanse, unable to support even the simplest forms of existence. The profound elegance of this moment lies in its simplicity. Hydrogen and helium, born from the cooling chaos of the early universe, were the ingredients from which all cosmic complexity would eventually emerge. With this foundation laid, the next chapter of the universe unfolds, revealing the hidden architects of cosmic structure. Moving forward, let us uncover the elusive yet profoundly influential role of dark matter in shaping the universe. Unlike the visible matter that makes up stars, planets, and everything we can see, dark matter is mysterious and invisible, interacting with regular matter only through gravity. Scientists cannot see it or directly detect it, but they know it must exist because of its significant gravitational effects on galaxies and other cosmic structures. In the chaotic, early days of the universe, dark matter acted as a kind of cosmic framework, a gravitational scaffold that helped pull gas and dust together to form the very first galaxies. Without its influence, the matter in the universe would have been too diffused to come together on its own, leaving a stagnant and lifeless cosmos. The exact nature of dark matter remains one of science's biggest mysteries. Some researchers theorize it could be made of yet-to-be-discovered particles that do not emit, absorb, or reflect light, making them invisible to our eyes and instruments. Despite its unknown origins, dark matter makes up a staggering 85% of all the matter in the universe. Its presence profoundly shaped the structure of the universe, influencing the formation and arrangement of galaxies into the intricate cosmic web we observe today. By acting as the invisible hand guiding the growth of cosmic structures, dark matter ensured that the universe would not remain a cloud of scattered particles, but would instead evolve into the breathtakingly complex entity we now strive to understand. As we consider this hidden cornerstone of the cosmos, the next chapter calls us to imagine the possibility of an even more expansive narrative. What if our universe is not the only one? With the next phase of the journey in sight, we arrive at a mind-bending possibility. What if our Big Bang was just one chapter in an infinite cosmic saga? The idea that our universe could be only one of countless others is not just a work of science fiction, but a real scientific hypothesis gaining traction among cosmologists. The multiverse theory suggests that beyond the boundaries of our observable universe, there may exist other universes, each with its own unique laws of physics, dimensions, and realities. These universes could have arisen from their own Big Bang events, independent of ours, or they might even coexist within dimensions beyond our comprehension. Another fascinating concept is the cyclical universe model, which proposes that the universe undergoes endless cycles of expansion and contraction. In this theory, a previous universe might have collapsed in a big crunch, giving way to the birth of our current universe in a new Big Bang, and this cycle could repeat indefinitely. These ideas stretch the limits of human understanding, but they also inspire profound questions. Could other universes harbor life or even civilizations unlike anything we can imagine? Could the multiverse hold answers to mysteries, such as why our universe has the specific conditions that allow life to exist? Although evidence for these theories remains elusive, scientists are actively searching for clues, such as unusual patterns in the cosmic microwave background, radiation, or signs of gravitational waves from potential collisions between universes. While definitive proof remains out of reach, exploring these possibilities expands the scope of what we know about existence itself, reminding us that the story of the cosmos may be far larger than we ever dared to dream. With these tantalizing questions in mind, we now shift our focus to a truly staggering revelation. The universe's earliest moments were marked by an expansion so rapid that it defies conventional understanding. With the next phase of the journey in sight, we delve into one of the most astonishing events in the universe's history, the phenomenon of cosmic inflation. Imagine this: in less than a trillionth of a second after the Big Bang, the universe grew from smaller than an atom to the size of a grapefruit. This event, known as inflation, marks a period of expansion so rapid that it surpasses our everyday understanding of speed. But how could something expand faster than the speed of light without breaking the fundamental laws of physics? The key lies in the nature of space itself. During inflation, it wasn't objects or particles moving through space faster than light. It was space itself expanding at an incredible rate. Think of it as dots on a balloon. When the balloon inflates, the dots move farther apart not because they are moving on their own, but because the surface they are on is stretching. This breathtaking burst of growth helped shape the universe as we know it, ironing out irregularities and explaining why the cosmos looks so uniform on a large scale, yet still contains the tiny variations that led to the formation of galaxies. Inflation also helps solve profound puzzles, like why distant regions of the universe appear to share the same temperature, even though they should be too far apart to have exchanged information since the Big Bang. This rapid expansion connected those regions, setting the stage for the universe's evolution. As staggering as this concept is, it deepens our appreciation for the mysteries of the cosmos and reminds us of the sheer scale and wonder of the forces at work in the earliest moments of existence. Moving forward, we look at how our telescopes allow us to peer back in time and witness the distant echoes of these ancient events. Now turning to the incredible power of telescopes, we uncover how tools like the Hubble Space Telescope have transformed our ability to explore the universe's earliest days. Imagine being able to look back in time billions of years to witness the cosmos as it was shortly after its formation. That's exactly what the Hubble Space Telescope has allowed us to do. One of its most groundbreaking achievements is the Hubble Deep Field Image, an extraordinary snapshot of a tiny patch of sky so seemingly empty that it might not catch the human eye. Yet, when the telescope focused on this small area for days, it unveiled thousands of galaxies, some dating back over 13 billion years. Each tiny dot of light in this image represents an entire galaxy, filled with countless stars and possibly planets, offering us a window into a time when the universe was still in its infancy. This discovery was nothing short of revolutionary, revealing not only how vast and populated the universe is, but also providing crucial insights into the structures and compositions of these primitive galaxies. By capturing light that has traveled billions of years across space, telescopes like the Hubble allow us to study celestial objects as they existed in the distant past, helping scientists piece together the timeline of cosmic evolution. What's most awe-inspiring about this is the sheer scale of time and distance involved, which reminds us just how small and fleeting our corner of the universe is. As we marvel at how far we've come in understanding these ancient galaxies, we now turn to the story of the first stars, giants that paved the way for everything we see around us today. Now turning to the universe's first stellar pioneers, we delve into the remarkable story of the earliest stars, known as Population 3 stars. These ancient giants were nothing like the stars we see today. They were far more massive, immensely brighter, and burned with an intensity that defies imagination. Their colossal size meant their lifespans were astonishingly short, ending in spectacular supernova after just a few million years, a blink of an eye in cosmic terms. But despite their fleeting existence, these stars played a monumental role in shaping the universe as we know it. In their fiery deaths, they forged the first heavy elements such as carbon, oxygen, and iron, scattering these building blocks across the cosmos. Without these elements, the formation of later stars, planets, and eventually life itself would have been impossible. These primordial stars acted as cosmic alchemists, transforming the universe from a simple composition of hydrogen and helium into a rich tapestry capable of supporting complex structures and systems. Their brief but profound lives laid the foundation for every star and planet that came after them, including the very atoms that make up our own bodies. As we trace the echoes of their contributions through time, their story reveals how even the most transient phenomena can leave an indelible mark on the cosmos. With this understanding of how these first stars set the stage for everything, we now move forward to uncover one of the universe's most perplexing and enduring mysteries, the question of its age and the challenges scientists faced in determining it. As the next challenge unfolds, we dive into one of the most perplexing puzzles in the history of cosmology, determining the universe's age. For much of the 20th century, scientists faced an unsettling contradiction. Early calculations suggested that the universe was younger than some of the oldest stars observed in the cosmos. This paradox posed a serious problem, as it is simply impossible for stars to exist within a universe that is younger than they are. These discrepancies stemmed from limitations in both our observational tools and theoretical models. For example, early estimates of the Hubble constant, which describes the rate at which the universe is expanding, were significantly off. This error led to an underestimation of the universe's age. Similarly, inaccuracies in determining the distances to celestial objects compounded the confusion. It was not until advancements in technology, such as the deployment of space-based observatories like the Hubble Space Telescope, that scientists were able to refine these measurements. By combining more precise data on cosmic expansion with observations of the oldest star clusters and the cosmic microwave background radiation, the faint afterglow of the Big Bang, they arrived at a much more accurate figure. Today, we estimate the universe to be around 13.8 billion years old, a number that aligns with the ages of the oldest stars and provides a coherent timeline for cosmic evolution. This journey of resolving conflicting data underscores the ever-evolving nature of science, where new discoveries continually reshape our understanding. With this clearer grasp of the universe's age, we can now delve into another fascinating enigma from its early history: the extraordinary emergence of colossal black holes in the infant cosmos. With the next phase of the journey in sight, we uncover the astonishing reality of the universe's first black holes, mind-bogglingly massive and shrouded in mystery. These early supermassive black holes, some weighing billions of times more than our Sun, appeared astonishingly soon after the Big Bang. Their rapid formation has left scientists grappling with one of the most profound questions in cosmology: how could such colossal structures arise in such a short cosmic timespan? Current theories struggle to explain this phenomenon. In the universe's infancy, matter was still in the process of clumping together under the pull of gravity, and yet these immense black holes somehow emerged with blistering speed. One possibility involves the direct collapse of vast clouds of gas, skipping the intermediate stages of star formation entirely. But even this idea leaves gaps in our understanding. Another hypothesis suggests that these giants formed through the merger of smaller black holes or the accretion of extraordinary amounts of matter at an unprecedented rate. Despite these theories, the exact mechanisms remain elusive. What we do know is that these titanic black holes likely played a pivotal role in shaping the first galaxies, anchoring them with their immense gravitational pull and influencing the distribution of matter in the early universe. They might have even driven the formation of the large-scale structures we observe today, acting as cosmic architects in a chaotic landscape. This tantalizing mystery reminds us of how much we have yet to uncover about the universe's early days. And speaking of mind-blowing cosmic puzzles, let us now turn to the geometry of the universe itself and why its surprising flatness continues to baffle scientists. Now turning to the geometry of the universe, let us unravel one of the most unexpected revelations in cosmology. The universe appears to be flat. At first glance, this might not sound particularly remarkable, but in a cosmic sense, it is a profound and perplexing discovery. Scientists use the term flat to describe the overall shape of the universe, meaning that it lacks any large-scale curvature. Think of it like an infinitely stretching sheet of paper. If the universe were curved, objects traveling in straight lines over vast distances would either converge, like on the surface of a sphere, or diverge, as they would on a saddle-shaped surface. However, all measurements to date suggest that the universe does not exhibit this kind of curvature. Instead, it behaves as though it is perfectly flat. What makes this so surprising is that the forces at work during the universe's chaotic infancy, gravity tugging everything together, while the energy from the Big Bang pushed everything apart, would naturally tend to create a universe that is either closed and curved inward or open and curved outward. Achieving a flat universe requires an incredibly precise balance between these competing forces, and many scientists liken it to balancing a pencil on its tip for billions of years without it tipping over. The odds of such precision seem astronomically small. This is where the theory of inflation enters the picture. Inflation proposes that in the universe's first fractions of a second, space expanded faster than the speed of light, stretching out any initial curvature to create the flat geometry we observe today. Even with this explanation, the flatness of the universe continues to raise questions. Why did inflation happen in the first place? What caused it to stop? And could there be other universes out there, shaped differently from our own? These are questions that push the boundaries of our understanding, making the flatness of the universe not just a surprising fact but an enduring puzzle. From the vast voids of space to its intricate geometry, the universe never ceases to challenge our perceptions. Speaking of mysteries that defy easy answers, let us now dive into the revolutionary concept of cosmic inflation and how it reshaped our view of the early universe. Now turning to the groundbreaking concept of cosmic inflation, let us unravel how it addresses some of the most perplexing mysteries about the early universe. Imagine observing the universe on the largest scales and noticing something extraordinary. No matter where you look, whether it is toward a distant galaxy in one direction or the cosmic microwave background light in another, the universe looks astonishingly uniform. This is known as the horizon problem, and it leaves scientists scratching their heads. How could regions of the universe that are so far apart and seemingly unconnected have the same temperature and properties? In a universe without inflation, there simply would not have been enough time since the Big Bang for these regions to exchange energy and reach this equilibrium. Enter cosmic inflation, a theory proposed in the early 1980s that suggests the universe underwent a period of rapid, exponential expansion in its very first fractions of a second. During inflation, space itself stretched so dramatically and so quickly that regions which were once close enough to interact were blown far apart, explaining the remarkable uniformity we observe today. Inflation does not just solve the horizon problem, it also helps explain the flatness problem that we discussed earlier. Remember that finely tuned balance required to make the universe flat, like balancing a pencil on its tip. Inflation stretches the universe to such an extreme scale that any initial curvature will be smoothed out, just like how a crumpled piece of paper looks flat when you zoom in far enough. This process helps account for why the universe appears flat to every measurement we make. What is astonishing is that a theory crafted decades ago to explain puzzling observations continues to hold up under modern scrutiny, offering a framework that reshapes our view of the universe's earliest moments. And yet, mysteries remain. What triggered inflation to start? What caused it to end? And could the ripples left by inflation be the seeds of galaxies, stars, and planets, including the one we call home? As we continue to investigate these questions, we find ourselves inching closer to understanding the remarkable processes that shape the cosmos. Speaking of those seeds of cosmic structure, let us now explore how the first galaxies arose from the aftermath of inflation, forming the building blocks of the universe as we know it. Now turning to the fascinating origin of galaxies, we delve into the moment when the smooth, uniform universe began to transform into something far more intricate. After cosmic inflation ended, the universe was filled with tiny fluctuations in its density. Imagine faint ripples in a vast ocean. These minute differences were not random. They were the result of quantum fluctuations during inflation, magnified to cosmic scales. Over time, gravity took hold of these denser regions, pulling surrounding matter toward them. As this process continued, these clumps of matter grew larger and denser, eventually collapsing under their own gravitational pull to form the first galaxies. These early galaxies were far from what we see today. They were chaotic, glowing masses of stars, gas, and dark matter, forming the basic architecture of the universe. What is extraordinary is that these initial formations, born from tiny imperfections in the early universe, laid the groundwork for the cosmic web, a vast interconnected network of galaxies and galaxy clusters stretching across the cosmos. Within this cosmic web, gravity worked like an invisible sculptor, carving out filaments where galaxies would thrive and leaving behind immense voids where galaxies are scarce. These structures are a testament to the unseen forces and ancient processes that shape the universe as we know it, offering us a glimpse into the grand scale of cosmic evolution. Speaking of evolution, let us now uncover the mystery of antimatter, a phenomenon that challenges our very understanding of why the universe is made of matter at all. Now turning to the mystery of antimatter, we confront one of the most perplexing questions in cosmology. Why does the universe consist predominantly of matter when science suggests it should contain equal parts of matter and antimatter? To understand this enigma, let us first explore the concept of annihilation. When matter and antimatter meet, they annihilate each other in a burst of pure energy, leaving no trace of their existence. According to current theories, the Big Bang should have produced equal amounts of both, resulting in a universe devoid of matter altogether. However, that is clearly not what we observe. Instead, we see a universe filled with stars, planets, and galaxies, all made of matter. So what tipped the scales? Scientists speculate that subtle differences in the behavior of matter versus antimatter, a phenomenon called charge parity violation, might hold the answer. This tiny asymmetry, though not yet fully understood, could have allowed a small surplus of matter to survive annihilation in the early universe, eventually leading to everything we see today. Experiments are underway to investigate this puzzle further, with the hope that unlocking the mystery of antimatter will not only explain the imbalance but also reveal deeper truths about the universe's origins. As we continue to explore these cosmic puzzles, we cannot help but marvel at the sheer complexity and beauty of the forces at play. Now, let us step into an even earlier moment in cosmic history, the first second after the Big Bang, a time so extreme that it defies everything we know about physics. Moving forward, the first second after the Big Bang was a moment of unimaginable transformation, where the universe underwent changes so rapid and intense that they challenge our very understanding of physics. Within the tiniest fractions of a second, the universe expanded from a size smaller than an atom to something incomprehensibly vast, a phase known as cosmic inflation. This inflation was so extreme and swift that it set the stage for the very fabric of space and time as we know it. At the same time, the universe was a seething, chaotic sea of energy, where temperatures reached trillions upon trillions of degrees. During this inferno, fundamental particles like quarks and gluons began to emerge from the intense energy field, but they were far from stable, constantly colliding and annihilating each other in a violent cacophony of creation and destruction. As the universe cooled ever so slightly in mere fractions of a second, these quarks started to combine, forming the building blocks of protons and neutrons. Meanwhile, the four fundamental forces that govern our universe, gravity, electromagnetic force, and the strong and weak nuclear forces, began to separate from a single unified force, each taking on their distinct roles in shaping the cosmos. This unimaginably brief moment set into motion the complex interplay of forces and particles that would eventually lead to atoms, molecules, stars, and all the structures we see today. It was a dance of raw energy and matter, so precise yet so chaotic that even the slightest variation could have resulted in an entirely different universe, or no universe at all. This first second of existence was not just the beginning of time, but also the stage on which the rules of nature themselves were written. As this extraordinary event unfolded, it laid the cornerstone for everything that would follow in the universe's grand story. Now, let us explore how these quantum ripples and fluctuations in that early cosmic sea went on to shape the vast structures of the universe as we see them today. Now turning to quantum fluctuations, we uncover one of the most astonishing aspects of the universe's origins. These tiny, seemingly random disturbances during the period of cosmic inflation played a monumental role in shaping the universe as we observe it today. To put it simply, quantum fluctuations are minute variations in energy that occur at the smallest scales imaginable within the fabric of space itself. During inflation, as the universe expanded at an extraordinary rate, these microscopic ripples were stretched to macroscopic sizes, imprinting faint irregularities into the otherwise uniform energy field of the early universe. These irregularities may have been minuscule, but their impact cannot be overstated. Over time, as the universe continued to expand and cool, gravity began to take hold of these imprints, amplifying them and causing the slightly denser regions to attract more matter. These denser pockets eventually became the seeds for the large-scale structures we see today, such as galaxies, clusters of galaxies, and the vast cosmic web that connects them. What is truly mind-boggling is that this vast, intricate architecture of the cosmos, spanning billions of light years, owes its formation to fluctuations so small that they existed at scales far below what we can physically measure today. In essence, these quantum quirks bridge the gap between the incomprehensibly small and the unimaginably vast, demonstrating how randomness at the tiniest levels laid the blueprint for the grand, organized structures we see when we look at the night sky. This connection between the micro and macro is a profound reminder of how the very fabric of our universe carries echoes of its earliest, most chaotic moments. As we marvel at this extraordinary interplay, we step deeper into understanding how these cosmic ripples set the stage for an interconnected universe, one where the delicate balance of randomness and order continues to inspire awe. Moving forward, let us delve into the cosmic web itself, a breathtaking tapestry of galaxies and dark matter that ties the structure of the universe together. Moving forward, we unravel the cosmic web, an awe-inspiring framework that serves as the backbone of the universe's large-scale structure. Picture an expansive network of filaments stretching across billions of light years, connecting galaxies, clusters of galaxies, and vast empty voids in a stunning cosmic tapestry. This intricate web is not just a poetic metaphor, it is a literal alignment of matter, shaped by the interplay of gravity and dark matter over billions of years. Galaxies do not float randomly within the universe. Instead, they congregate along these vast filaments where dark matter acts as an invisible scaffold, holding this grand structure together. Between these filaments lie immense regions of near emptiness known as cosmic voids where very little matter exists. What is truly breathtaking is the scale. This web spans distances beyond human comprehension, yet its intricate design reveals the organized chaos of the universe's early development. It all began with those quantum fluctuations we just explored. The denser regions created by those fluctuations seeded the growth of mass, and as gravity exerted its pull, matter began to flow toward these regions, stretching and connecting them into the web-like structures we observe today. Supercomputers simulating the evolution of the universe have brought this cosmic network to life, revealing its striking resemblance to neural networks or even the structure of a living organism, hinting at a profound interconnectedness within our cosmos. What unites all of this is dark matter, the mysterious and invisible substance that makes up most of the mass in the universe. Though we cannot see it directly, its influence is undeniable, shaping the flow of normal matter into these filaments and voids. The cosmic web is a reminder of how the universe is not a random scattering of objects but a deeply interwoven masterpiece, where every galaxy, star, and planet finds its place within a larger structure. As we marvel at this immense network, it becomes clear that the story of the universe is one of connection and balance, where even the most distant corners are tied together by unseen threads of gravity and dark matter. With this newfound appreciation for the interconnectedness of the cosmos, let us now shift our focus to the first light that illuminated this grand web, marking the dawn of a transparent universe. With the next phase of the journey in sight, let us uncover the story of the first light that pierced through the darkness of the early universe. After the Big Bang, the universe entered a period often referred to as the cosmic dark ages. During this time, the universe was filled with neutral hydrogen gas, and while matter had begun to clump together under the influence of gravity, there was no light capable of escaping this dense fog. This all began to change with the appearance of the very first stars, a monumental event that sparked the era of cosmic reionization. These early stars, massive and short-lived, shone with incredible intensity, emitting powerful ultraviolet radiation. This radiation started to break apart the neutral hydrogen atoms, ionizing them and gradually turning the opaque universe into a transparent one. As more stars and galaxies formed, their combined energy amplified this process, carving out pockets of light and clarity within the cosmic fog. Over a span of hundreds of millions of years, these pockets expanded and merged, eventually reionizing nearly the entire universe. This reionization not only marked the end of the Dark Ages, but also set the stage for the universe to take on its current form, where light can travel freely across vast distances, allowing us to observe the cosmos as it was billions of years ago. The first light and the process of reionization stand as a symbolic dawn for the universe, illuminating the intricate structures we now study and admire. It is a reminder of how far the universe has come since its chaotic beginnings, forever transforming our cosmic landscape. With this in mind, let us delve deeper into the forces that have shaped the universe's evolution and continue to govern its grand design. Now turning to the invisible architect of the universe, gravity has been the fundamental force shaping the cosmos since its earliest moments. From the chaotic aftermath of the Big Bang, gravity began its relentless work, pulling particles together to form the first clumps of matter. These clumps grew larger over time, eventually giving rise to stars, galaxies, and the vast cosmic structures we observe today. It is gravity that binds stars into galaxies and holds planets in orbit around their suns, creating the celestial dance that defines our universe. But the story of gravity does not end there. While it acts as the great unifier pulling matter together, it is in constant tension with dark energy, a mysterious force that drives the universe to expand at an accelerating rate. This cosmic tug of war between the attractive force of gravity and the repulsive push of dark energy has defined much of the universe's evolution. Gravity may have dominated the early universe, but as it expanded, dark energy began to take center stage, accelerating the expansion and dictating the universe's large-scale structure. This ever-present interplay continues to shape the cosmos, influencing not only its past but its future as well. Gravity, though familiar to us in our everyday lives, holds an extraordinary and far-reaching role in the grand design of the universe, weaving together the stars, galaxies, and clusters that form the fabric of existence itself. As we embrace this profound understanding, let us move forward to explore another surprising revelation that alters our perception of the cosmos. With the next phase of the journey in sight, let us delve into the remarkable discovery that the universe is not only expanding but doing so at an accelerating rate. This groundbreaking revelation came in the late 1990s when astronomers studying distant supernovae observed that these exploding stars were farther away than previously expected. This unexpected distance indicated that the universe's expansion was speeding up rather than slowing down, as many had assumed. The force driving this accelerated expansion has been attributed to dark energy, a mysterious and little understood phenomenon that makes up roughly 70% of the cosmos. Unlike gravity, which pulls objects together, dark energy works in opposition, pushing the universe outward and causing space to stretch at an increasing pace. This revelation did more than just upend our understanding of cosmic evolution. It posed profound questions about the ultimate fate of the universe. Will dark energy continue to dominate, leading to a cold, ever-expanding cosmos where galaxies drift so far apart that they become isolated islands in an infinite void? Or could the nature of dark energy change over time, perhaps slowing its effects or even reversing them? These questions have sparked some of the most exciting research in modern cosmology, as scientists strive to unlock the secrets of this enigmatic force. The accelerating expansion has reshaped our conception of the universe, reminding us that the cosmos is a far stranger and more dynamic place than we could have ever imagined. As we reflect on this profound transformation in our understanding, let us turn our attention to yet another cornerstone of the universe's story, one that further enriches our view of its vast and intricate tapestry. Now turning to the history of the Big Bang Theory, we find a story not of immediate acceptance but of significant skepticism and debate. In the early 20th century, the prevailing belief among many scientists was that the universe was eternal and unchanging, a concept known as the steady-state model. The idea of a universe with a dynamic beginning was unsettling and, to some, unscientific. In fact, the term Big Bang itself was coined by astronomer Fred Hoyle during a radio broadcast in the 1940s as a dismissive criticism of the theory. Hoyle and other proponents of the steady-state model argued that the universe could simply replenish itself with new matter, maintaining its constant appearance while avoiding the implications of a singular origin. Yet, as observational technology improved and evidence accumulated, the scales began to tip in favor of the Big Bang theory. One of the most compelling pieces of evidence came with the discovery of cosmic microwave background radiation in the 1960s. This faint, all-encompassing glow was exactly what the Big Bang theory predicted: a remnant heat from the universe's fiery birth, spread uniformly across the cosmos. Coupled with Edwin Hubble's earlier observations of galaxies moving away from each other, indicating an expanding universe, the evidence became increasingly irrefutable. While it took time for the scientific community to embrace the idea, these discoveries ultimately established the Big Bang not just as a plausible explanation but as the leading cosmological model. It transformed our understanding of the universe, showing us not a static, unchanging cosmos, but one with a beginning, a history, and a trajectory. With the controversy surrounding its acceptance now behind us, the Big Bang theory stands as a testament to the power of evidence and observation to reshape even the most deeply held beliefs about the nature of reality. Moving forward, let us delve deeper into the poetic connection between the universe's origins and ourselves, uncovering how the elements that compose our very bodies trace back to the stars themselves. Moving forward, let us uncover one of the most profound truths about our existence. We are quite literally made of stardust, the very carbon that forms the backbone of organic life, the oxygen we breathe, the calcium in our bones, and even the iron in our blood all trace their origins to the cores of ancient stars. Billions of years ago, these massive stars underwent nuclear fusion, a process that forged heavier elements from simpler ones like hydrogen and helium. When these stars reached the end of their life cycles, many exploded in spectacular supernovae, scattering their enriched contents across the cosmos. These elements then became the building blocks for new stars, planets, and ultimately life itself. This means that every atom in your body was once part of a star that lived, burned, and died long before our solar system even existed. It is a poetic and humbling reminder of our connection to the universe, showing that we are not separate from it but intrinsically linked to its history. As we marvel at the stars in the night sky, we are, in a way, looking at our own origins, a cosmic family tree that binds us to the very fabric of the universe. Let us now turn our gaze toward the ultimate fate of this universe, exploring how its ending might mirror the story of its birth. Now turning to the ultimate fate of the universe, we enter a realm of theories that are as fascinating as they are complex. Just as the universe had a beginning, it will eventually have an ending, and the possibilities for how this will unfold seem to echo its origins in remarkable ways. One theory, known as the Big Crunch, suggests that the universe's current expansion might one day reverse due to the pull of gravity. Imagine all the galaxies, stars, and planets gradually moving back toward one another, eventually collapsing into a dense, hot point, much like the state believed to exist before the Big Bang. It is a cycle that could lead to another universe being born anew. On the other hand, the heat-death scenario presents a different, quieter end. According to this idea, the universe will continue expanding indefinitely, but as it does, stars will burn out, galaxies will drift apart, and all matter will eventually reach a state of maximum entropy. This would leave the universe cold, dark, and devoid of any usable energy for sustaining activity. Then there is the Big Rip theory, a scenario where the mysterious force driving the universe's accelerated expansion, known as dark energy, could grow so powerful that it tears apart everything: galaxies, stars, planets, and even the very fabric of space itself. Each of these theories paints a different picture, yet they all reflect intriguing parallels to how the universe began. From an extremely dense point to rapid expansion to the formation of complex structures. Whether through a fiery collapse, a slow fade into stillness, or a catastrophic unraveling, the end of the universe might in some way bring us full circle, tying the story of its origins to its ultimate destiny. This exploration of cosmic endings is not just a scientific curiosity, but a profound reminder of the vastness and mystery of the cosmos we inhabit. With the next phase of the journey in sight, let us delve into the deeper implications of the universe's potential fate and what these scenarios mean for our understanding of existence itself. Each theory about the universe's end, whether it be the Big Crunch, heat death, or Big Rip, does more than outline a possible final act. It forces us to reflect on the nature of beginnings and endings, change and permanence, and our place in this vast continuum. The idea of the Big Crunch, for example, challenges us to consider the possibility of a cyclical cosmos, where creation and destruction are not opposites but interconnected stages of an eternal process. This perspective mirrors ancient philosophies that viewed the universe as a perpetual cycle, endlessly renewing itself. On the other hand, the notion of heat-death prompts profound existential questions. If all energy and activity ultimately fade into silence, what does that say about the fleeting nature of everything we know and value? It is a humbling reminder of the impermanence of not just human life, but the very fabric of existence itself. The Big Rip, with its dramatic vision of reality tearing apart at every level, highlights the fragility of the universe and the mysterious forces that govern its destiny. These theories do not just look forward, they also compel us to look back. If the universe's end holds echoes of its beginning, then understanding one could illuminate the other. Did the dense, hot state before the Big Bang arise from a previous collapse? Does the accelerating expansion we see today hint at a future unraveling? By exploring these questions, we gain a deeper appreciation for the cosmic story we are part of. More personally, contemplating the universe's vast timeline and its eventual fate can inspire a renewed sense of wonder, urging us to cherish the unique moment we inhabit. While the universe's end may seem distant, it ties us to a larger narrative that spans eons and invites us to see ourselves not just as spectators but as participants in a grand, unfolding mystery. These reflections make the study of cosmic endings not merely a scientific pursuit but a profound exploration of existence itself. Moving forward, let us unravel the intriguing concept of the universe's flatness, a property that has left scientists both amazed and puzzled. When researchers say the universe is flat, they mean that, on the largest scales, the geometry of space does not curve inward like a sphere or outward like a saddle, but instead stretches endlessly in a straight, flat plane. This result is so counterintuitive because of the sheer complexity and interplay of forces that have shaped the cosmos since the very beginning. Think about it. The universe's geometry is determined by an incredibly delicate balance of density, energy, and expansion. If the total density of matter and energy in the cosmos had been even slightly higher or lower at the start, the universe would have either curved into a closed, spherical shape or expanded into an open, saddle-like one. The fact that we observe the universe as flat suggests that, remarkably, it was precisely balanced, a phenomenon scientists often compare to a pencil standing perfectly upright on its point. But how could such a fine balance have been achieved? This is where alternative theories step in to provide possible explanations. One leading idea is the theory of cosmic inflation, which posits that the universe underwent an unimaginably rapid expansion in its earliest moments. This inflationary phase would have smoothed out any initial irregularities and driven the universe toward flatness, much like how blowing up a balloon makes its surface appear flatter the larger it becomes. Yet, even this solution raises further questions. Critics wonder whether inflation itself requires an equally fine-tuned set of conditions to work as proposed. Others suggest that our perception of flatness could arise because we are only observing a tiny portion of a much larger and possibly more complex cosmic structure. Could the universe be flat only within our observable horizon, while its true shape remains hidden beyond reach? The idea of a multiverse further complicates things, suggesting that different regions of a vast cosmic landscape might have wildly varying geometries, of which our flat universe is just one example. These alternative theories highlight the profound mysteries surrounding the universe's geometry, encouraging us to keep questioning and exploring. With so much still unknown, the flatness of the universe serves as both a clue and a challenge, reminding us of the intricate forces and conditions that make our existence possible. As we continue to probe these fundamental questions, we deepen our understanding of not just the cosmos but the extraordinary precision of the mechanisms that govern it. Now turning to the tantalizing question of whether we could ever detect other Big Bang events, we enter a realm that challenges both our imagination and the limits of our scientific tools. If the multiverse theory holds any truth, it suggests our universe is just one bubble in an endless cosmic sea, each bubble representing its own universe with potentially distinct laws of physics and initial conditions. But how would we even begin to glimpse evidence for such an extraordinary idea? Scientists have proposed several fascinating methods to seek out these cosmic clues. One intriguing avenue is to search the cosmic microwave background radiation, the faint afterglow of our own Big Bang, for subtle anomalies. Some theories predict that if our universe collided with another during its inflationary phase, it could leave behind telltale imprints, such as faint circular patterns or temperature irregularities. These marks would act like cosmic fingerprints, hinting at interactions with neighboring universes. Another approach involves looking for gravitational waves, ripples in space-time caused by violent cosmic events. If multiple Big Bangs occurred, they might have produced a unique spectrum of gravitational waves that could still be detectable today, offering indirect evidence for such events. Additionally, advanced computational simulations are being used to model multiverse scenarios, exploring how different universes might interact or diverge from one another. These simulations aim to predict what observable effects, if any, could emerge in our own universe. However, the search for evidence of other Big Bangs is not without its challenges. The observable universe places a hard limit on what we can study, as light and other signals cannot travel faster than the speed of light to reach us. This cosmic horizon means that any universes beyond this boundary remain fundamentally inaccessible to direct observation. Even so, the pursuit of these questions is far from futile. Each experiment, each observation, and each new theory helps refine our understanding of not just our own universe, but the incredible possibilities that might lie beyond. The idea that we could someday detect echoes of other Big Bangs is both exhilarating and humbling, reminding us that the cosmos is far richer and stranger than we can currently comprehend. As we push the boundaries of our technology and our thinking, the answers may one day reveal themselves in ways we can scarcely imagine. And this relentless drive to uncover the unknown is what makes the exploration of the universe's origins so profoundly inspiring. Moving forward, let's delve into the fascinating implications of a universe without an edge or center. Imagine standing on the surface of a spherical Earth. No matter which direction you walk, you will never find an edge. Similarly, in the context of our universe, space might curve back on itself in a way that defies our everyday understanding of boundaries. This concept challenges the human mind, as we are accustomed to thinking of space as something that must have limits. If the universe truly has no edge, it forces us to reconsider how we perceive infinity. Does infinity mean endless space, or could it mean that space loops back around, creating a finite yet unbounded cosmos? This idea isn't just a mathematical curiosity, it also raises profound philosophical questions about existence itself. One such question is whether an infinite universe implies infinite possibilities. If there are no edges, could there be endless versions of you out there, experiencing variations of your life in other distant regions of space? Another intriguing aspect is the nature of cosmic expansion. Without a center to pinpoint, does this mean the universe expands everywhere simultaneously, like the surface of a balloon inflating? This challenges our intuition, which tends to seek definitive locations and starting points. A universe without an edge also means that the idea of where it all began becomes even more abstract. If space is isotropic, meaning it looks the same no matter where you are, then every point can be considered the center from its own perspective. This reshapes how we interpret the origins of the cosmos and our place within it. Additionally, the absence of edges could have implications for how we think about time. In an infinite or looping universe, does time also repeat or extend infinitely? The concept of edges and boundaries isn't just about physical space. It ties directly into our understanding of the passage of time and the very fabric of reality. This boundless nature of the universe forces us to confront the limits of human comprehension. It invites us to step outside the comfort of our finite experiences and grapple with the vastness of a cosmos that may have no measurable end. Such an idea might seem unsettling at first, but it also offers a profound sense of wonder. It reminds us that our journey to understand the universe is not just about seeking answers, it is about embracing the mysteries that deepen our connection to the cosmos itself. Now turning to the mystery of antimatter, let's explore why it might hold the key to understanding the universe's origins. When the universe was born, scientists believe matter and antimatter were created in nearly equal amounts. However, what puzzles researchers is that our universe overwhelmingly contains matter, while antimatter seems to have all but vanished. This imbalance defies what we would expect from the symmetry of the laws of physics. Antimatter, in simple terms, is like the mirror image of matter. For every particle of matter, there's an antimatter counterpart with the same mass but opposite charge. When these two meet, they annihilate each other, releasing pure energy. So why wasn't everything wiped out in the early universe, leaving nothing but energy behind? Some subtle difference between matter and antimatter must have tipped the scales, but scientists are still searching for answers. Experiments like those conducted at massive particle accelerators are shedding light on this enigma. By creating and observing antimatter particles, researchers are comparing how they behave alongside their matter counterparts. One such breakthrough experiment found slight differences in how certain particles decay, suggesting that this asymmetry, though tiny, could be the key to why matter triumphed over antimatter. Solving the antimatter mystery could rewrite our understanding of the Big Bang because it directly ties to how the universe evolved into a space filled with galaxies, stars, planets, and life, instead of just a lifeless void. It also opens up futuristic possibilities. Harnessing the energy from matter-antimatter reactions could revolutionize technology. The stakes of this research are immense, as every new discovery brings us closer to unraveling the puzzle of why we exist. But the journey doesn't stop here. As we conclude this exploration of 25 forgotten facts about the universe's origins, it becomes clear just how much these revelations reshape our understanding of the cosmos. From the groundbreaking discoveries of the Big Bang's subtle intricacies to the mind-bending mysteries of dark matter, antimatter, and the universe's flatness, each fact challenges what we thought we knew and opens up entirely new realms of questions. These insights remind us that the story of the universe is not a closed book but an evolving narrative, one that we are only beginning to understand. They show us how deeply connected we are to the cosmos, from the hydrogen and helium forged in the universe's first moments to the stardust that makes up our very being. The universe's journey from a hot, dense plasma to the ever-expanding network of galaxies we see today is nothing short of awe-inspiring. And as we grapple with its future, whether it ends in a big crunch, heat death, or something else entirely, we are reminded of how intertwined its fate is with its origins. So, as we wrap up, I invite you to stay curious. Keep questioning the universe, for every answer sparks a dozen more questions. If you enjoyed this journey through the mysteries of the cosmos, subscribe to our channel and join our growing community of cosmic explorers. Share your thoughts in the comments, whether it's your own cosmic questions or what you found most fascinating about today's video. And don't forget to like the video and hit the notification bell so you never miss an update as we continue unraveling the mysteries of the universe together. Until next time, keep looking up and wondering what else the cosmos has in store.